In this section, we're going to extend the definitions of integrals. So far, if you'll remember, I'm not sure if I remember the spelling on Riemann. I don't even know if it's Riemann or Riemann, but I think there's two N's. Whatever the case may be. It might be two M's for all I know. Riemann integrals never have unbounded intervals or unbounded regions of integration. So the most typical case for a Riemann integral looks like this. You would start, you don't have to start and end here, but the function goes through these points, goes through those values, and it's a continuous function. And as long as the function is continuous, or at least not so broken up that you can measure area underneath each of these things, the Riemann integral will report the area under there. We'll do other things besides that, but and you've seen based on the volumes and things like that, stuff that it will do. What do we do though? What happens? What do we do now? Let's say something like this. Let's start with an integral that starts, let's start it at a, but then it goes off to infinity, say. Well, we have to work with that. And what we do is this. For everything here, for this video, all the functions will be continuous except as noted. So we're not going to be dealing with a lot of breaks, but the breaks that we will be dealing with are of substantial importance. So anyways, what we do is this. To evaluate a function like this, where it starts at a and goes off to infinity, this notation, we define it as this. What we do is we define it as a limit, and the limit is as b goes to infinity, a to b. So now I'm dealing with this situation here, so I'll get an answer before I take the limit, but then the limit will deal with whatever b was, and that's how we'll evaluate these things. So let's do some examples, or let me first consider a function, then we'll do some examples. Consider y equal x to the negative 1/2, or if you prefer, y equals 1 over radical x. Now if you go and graph that thing, here's the basic shape of the graph. It's only defined when x is positive, and it'll go like something like this. It'll tend to the x-axis as x goes to infinity, and it will go off to positive infinity the closer that x gets to the y-axis. So, does it make sense to measure area under here? Will it even have an answer, or is that area always going to be infinite? Well, we're going to break this up. Before I talk about this piece right here, I'm going to first talk about, say, a number. Doesn't have to necessarily be 1. It could be the letter a if I wanted to. But this is the area I'm going to concern myself with right now. Will that possibly be reasonably considered finite? And the way we might try to see is to determine if the integral from 1 to infinity 1 over the square root of x dx, which equals the limit as b goes to infinity, the integral of 1 to b x to the negative 1/2. I'm just rewriting it there. And now, the reason why we put the 1 to b is because now I'm going to evaluate this as I normally would any other integral. But I'm going to keep this out here because it will be, I'll apply that as my last thing. So we'll take, add 1 to this will be x to the 1/2 over 1/2, and this is 2x to the 1/2. And that's going from 1 to b. So I'm going to plug in the limits before I take this limit. I should call it the endpoints of the interval before I take this limit. So what I'll have then is I'll plug in b, and then I'll subtract where I plug in 1. You should know that if this power is positive, this part here automatically goes to infinity. The limit of a constant is not important because it's just that constant. So I'll get infinity minus 2. Well, it's still infinity. So what happens is this thing right here, because the limit failed to exist, we say that diverges. That's the key phrase, diverges. If the limit exists, we say that it converges. Now, what we need for convergence, so let's see, we want the limit, converging integrals. Maybe I'll say this. What are those that converge? Well, that's anytime any of these limits exist. So if I go from a number to infinity of the function, if that, and remember, this is a limit. So this integral is considered converging if this limit exists. I can go the other way too. I can do something like this. I could have a b up here, but then negative infinity to b. And that's defined in a similar manner. If it's the limit, you'd use an a down here, I suppose. But the complicated one is the following. If I have from negative infinity to infinity, I have to break it up. Watch this. This will be the limit as a goes to negative infinity of a to c f of x dx plus a second limit. This time b goes to infinity. I'm using different letters just for the purposes of making you understand that these are separate limits. If this is considered to converge if both of these limits exist. So both integrals must exist. Notice I'm using a different letter just to really drive that point home. Let's do an example to illustrate what I'm talking about. I'm going to start with my first example, be the integral from negative infinity to infinity, 1 over 1 plus x squared dx. Now you know the antiderivative of 1 plus x squared probably by heart now. That's arctangent of x, and we could write negative infinity to infinity. However, what we need to do is arctangent of x from negative infinity to, I don't know, some number 8. You can pick whatever is convenient for yourself, so you can put a 0 there if you want. Plus arctan x 0 to infinity. Now each of these has to exist. Let me write more details. Really, this is the limit as a goes to negative infinity of arctangent of x from a to 0 plus the limit as b goes to positive infinity arctangent of x from 0 to b. Now let me throw in my numbers. So this will be the limit as a goes to negative infinity tan inverse of 0 minus tan inverse of a, plus the second piece will be very similar. It will be the limit as b goes to infinity tan inverse of b minus tan inverse of 0. Now what's going to happen if everything is on the up and up and all these limits exist and things like that, this part where you break the two pieces up are going to cancel each other anyways. You'll see. What is arctangent of 0 but 0? Now as a goes to negative infinity, arctangent goes to negative pi over 2. Now as b goes to infinity, arctangent goes to pi over 2. And tan inverse of 0, which is, by the way, these tan inverses of 0 are unaffected by the limit. They are just constants. Here I'm going to get minus 0. Well, not that it matters here, but 0 minus 0 is 0. But these are the important things. The pi over 2's give us pi. So that means that we actually have, mathematically at least, an area under there. Let me draw a graph of this real quick. What you have is something of a bell-shaped curve that does not, this somehow comes out to add up to pi. That's sort of, this is a large deal here. Now you're talking about something unbounded, but nonetheless, the area accumulates in such a way that it's slower than anybody could sort of keep track of it. So somehow the area adds up in such a slow rate that we consider it addable, at least from a mathematical sense. And it's all based on these limits. Remember, every important concept in calculus is based on a limit, so this makes no difference. Most of the integrals I'm going to do in this section are kind of generalized things, but I'll do some concrete examples near the end here. So what I'm going to do here is for the integral of e to the negative ax from 0 to infinity, I'm allow a to be any positive real number. So accordingly, when you take the antiderivative of e to the negative ax, I think I'm going to, I don't think I need to do it, but I will. U is going to equal negative ax, and then du will equal negative a dx. And I'll divide by negative a, so that this integral then, well, let's throw our numbers in then. If I put a 0 in for x, it still will be 0 here. Let me put the negative 1 over a out front because it will appear there at some point anyways. Now, if I plug in infinity, if you let x go to infinity, this part will go to negative infinity. Because a is positive, this piece right here, negative a, is guaranteed to be negative. If x is going to positive infinity, that means x is going to very big numbers. And just recall your calculus 1, this will go to negative infinity. And then I'll have e to the u du. Of course, that will equal negative 1 over a e to the u from 0 to negative infinity. If you wanted to, you can flip and take this negative out. Like I can rewrite this as 1 over a e to the u from negative infinity to 0. Of course, now this is the worst thing that could happen, at least from a teaching standpoint, that the lower limit is the one going to negative infinity, and this is the letter I like to use as a for that. So I'm going to have to come up with something different. Let's do the limit. Let's go c goes to negative infinity, 1 over a e to the u from c to 0. Now let's throw our numbers in. I will have 1 over a e to the 0 minus 1 over a e to the c, but c is the one doing the moving. If c is going to negative infinity, remember the graph of e to the x, just a real quick graph of e to the x goes like this. Let's say that's y equals e to the x. I mean, as x goes to infinity, it shoots off to infinity big time. But as x goes to negative infinity, that piece goes to 0. So we'll have the limit. Oh, I'm taking the limit out now. I don't need the limit for this part. This part will just be 1 over a. But this piece here will be 0. Since a is positive, this number is defined. And if this piece is going to 0, then something going to 0 times the number is still going to go to 0. Many times we're interested just with the convergence of an integral, and this one does because this number exists. The limit exists. I don't know what p is, but my intent is to define the values of p for which this does converge and which it doesn't. Whenever you're integrating something like this, it's usually way easier to put it in exponential notations that we can use the power rule. Of course, the rule goes like this. Add 1 to the exponent and divide by that same new exponent. This is going from 1 to infinity. This, of course, is the limit. As b goes to infinity, b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 all over negative p plus 1. This part right here is just constant, so I'm going to break it out of this limit because I don't want it hampering my discussion. In here, don't think these negatives cancel. I don't know what p is. I haven't figured that out yet, so p could be positive, negative, whatever. I'm still working on that one. So as long as p is not equal to 1, this is going to be fine. So I could write this answer here And it's not part of our discussion as far as the limit is concerned. Now, now I want to talk about the values of p for which this does and doesn't exist. The negative p plus 1 is just a constant unless p equals 1. We'll handle that case completely separate. So this part here is a constant. I'm going to pull it out. I think it may help everybody if I rewrite it as 1 minus p instead. Let's take a look. So I'm not going to put in 1, but let's talk about numbers bigger than 1 and less than 1 and equal to 1 and see what actually happens now. Now, if b is going to infinity, the only way this is going to actually converge is if this thing is negative. The exponent is negative. If the exponent is positive, this part will go to infinity. So let me write that. So if p is such that this piece is negative, then this will go to 0. So that'll equal 0 if p ends up being greater than 1. Because if p is greater than 1, this is a negative number. P equals 1 will be taken care of later. I won't even do the integration to deal with that part. Will I? No, I will. It's not quite this simple. Then if p is less than 1, what happens? Well, if p is less than 1, isn't it true then that this is a positive number? If this is a positive number, then any number that's going to infinity to a positive power will equal infinity. What that means is that the integral x to the negative p dx from 1 to infinity converges. If p is greater than 1. And it diverges if p is less than 1. That's pretty simple. Now, however, for p equals 1, we do the integral 1 over x dx from 1 to infinity, and that of course is the natural logarithm. I don't have to put the absolute value because 1 to infinity is a positive domain. This of course be the limit as b goes to infinity of ln of b minus ln of 1. It doesn't matter if I put that in parentheses or not because it's a constant. Ln of 1 is 0, but this piece right here, natural logarithm function, while it may not break any speed records, it does tend to infinity as b goes to infinity. So we can throw in, so it's going to become infinite if p equals 1. So it's going to diverge if p is less than or equal to 1. Of course, this is a monster concept for the book and for this section. Now, an interesting comparison involves intervals that have a 0 in them. They are, in a way, kind of like a flip side to infinity. I mean, think about how many things you think of this way. If I take 1 over infinity, you think of that as 0. Or something over a very large number is getting closer to 0. Turn it upside down, and now it's infinity. So the two are very closely related. I want to look at the same function, but this time from 0 to 1. Now, 1 is no big deal like it wasn't before, but 0 is a huge deal because no matter what, 0 x equals 0 is a vertical asymptote. So if I'm going up to 1, I'm going to try to figure out if there's area actually inside of there up to 1, even though it's unbounded. It's the infinite area, but I don't want to say an infinite area. I want to say it's an unbounded area, but somehow it's finite. I'm going to do exactly the same stuff I did before, and then I'll consider the cases like I did before as well. So this, of course, is x to the 1 minus p over 1 minus p, and that's going to go from, the 1's not the big thing here. You can plug that in easy enough. But this down here is the hard part. I'm going to do the limit as a goes to 0, but from the right, because it's between 0 and 1. That means it's greater than or equal to 0 throughout the whole problem. So I can only approach 0 from the right-hand side. This typically is not going to be a big deal other than dealing with radicals and things where that matters. So let's see what happens. We have the limit as a goes to 0 from the right. I'll have 1 to the 1 minus p all over 1 minus p minus a to the 1 minus p divided by 1 minus p. And once again, this part is of no consequence. It's easy enough to do. We have 1 to the 1 minus, I don't need the 1 minus p, that's just going to be 1, but I'll have it in the denominator. I'll have 1 minus p in the denominator, minus Now, how do these limits work out? Now, as long as this exponent is a positive number, then I can just plug a equals 0 in, and you get 0. So this will equal 1 over 1 minus p minus 0 if 1 minus p is positive. Well, if 1 minus p is positive, that means 1 minus p is greater than 0, which means that 1 is greater than p. So when 1 is greater than p, I'll have 1 over 1 minus p. And then go back to that. Now, this time, if 1 minus p is negative, well, think of something like x to the negative 2 or x to the negative 1. Or if it's negative, I can rewrite it as 1 over a to the p minus 1. Well, what happens then is that 0 will be an asymptote. X equal to 0, or the y asymptote will end up being an asymptote. And this will go to infinity. I think I don't know if I talked, well, oh no, sorry. I don't have to. A is a non-negative number throughout this whole problem. So that means that I have positive numbers that are getting close to 0 with a negative exponent. So you think of 1 over this small number, it's getting close to infinity. And this, of course, equals negative infinity. Well, it just means that we have divergence in that case. And then for p equal 1, we're still dealing with this. I don't need absolute values again because I'm not dealing with negative numbers. Well, you know that the natural logarithm a, if you go to 0 from the right-hand side, the graph of ln of x goes shooting down to negative infinity. So this equals 0 minus negative infinity equals infinity. So here's what we have then. The integral from 0 to 1 over x to the p dx converges p, remember I said when p is less than 1, diverges when p is greater than or equal to 1. And notice if you compare that to the other one, the situations are completely reversed. The other one converged when p was greater than 1. So that's why I said they're flip coins of the same coin, actually. Very intimately related are 0 and infinity. It's impossible, actually, to separate them because of this. So just a quick examples of this. If I gave you 1 to infinity, 1 over x to the third dx, would that converge or diverge? That's convergent. Three is greater than 1. However, if it's x to the 1/2, that diverges because the exponent is less than 1. On the other hand, if I instead did 0 to 1, 1 over x cubed dx, now that thing diverges for the very same reason, because 3 is greater than 1, and that integral converges. X to the 1/2 dx converges because 1/2 is less than 1. Notice that exponent to the 1 never converges in any of these scenarios. One of the things you ought to know is that the limit as x goes to infinity, e to the ax equals infinity if a is greater than 0 and equals 0 if a is less than 0. The graph of e to the ax is always going to look something like this. If a is, it just depends on what a is, positive or negative. But e to the ax will be something like this. That means as you go to infinity, it'll be infinite. The other direction will be 0. You could flip this around by changing a to positive or negative, and it will simply reflect this graph about the y-axis, and you'll have an opposite thing occurring. That's important for some of the stuff we're going to do. Another one that you should know is that the limit as x goes to any infinity of any of our trig functions, none of them exist. I'm not talking about inverses. I'm talking about your basic ones: sine, cosine, secant, the 6 big ones. None of these exist as you go to infinity because they are cyclic. Being cyclic like that, they will increase and decrease in the amount of area they accumulate as x goes to infinity. So none of these will hone in, if you will, on a particular value. Well, with this in mind, let's do an example. Let's do x e to the negative x squared from negative infinity to infinity. This is like doing 2 examples at once because I have to do 2 integrals at once. And in this case, you would let u equal negative x squared, and then du would equal negative 2x dx. Now, I didn't need the negative 2, but I have an x and I have a dx, so I'm going to divide by that negative 2 and put a negative 1/2 there. Now let's plug in our limits of integration. This is an odd thing to do. If you put in negative infinity, like you can put it in here, what happens when you square a negative number? It becomes positive. But then the negative in front of it will make it negative. So what I'm saying is the negative infinity will still be negative infinity. However, if you take this infinity, plug it in, I have quote fingers going on, plug it into here, this would also be an infinity, but the minus would make it a negative infinity. Now, what are you supposed to do with that? Any integral with the beginning and ending that would be exactly the same would end up being 0. Now, this should tell you that the substitution you're doing is not working right if you simply wipe out the problem in this manner. So this, it's not that that was a bad substitution. No. What I'm going to do is remind you that we have to break this into two integrals to consider whether it's existing or not existing. So what I'm going to do is we're going to rewrite this problem as the following. I'm still going to use this. This is not bad. It's just I have to apply it to two integrals. One, we can go from negative infinity to 0. You can choose. This doesn't have to be 0, but whatever's convenient. 0 usually is very convenient. And then I'm going to add to it from 0 to infinity x e to the negative x squared dx. I will use exactly the same u for both of the problems, and we'll see what happens here. So my u for this one has a negative x squared. Negative infinity will still have a negative infinity there. If I plug 0 into x squared, u will be 0. And then I'll have a negative 1/2 du, and that will be the x dx part. So I'll have e to the u du. Same deal over here. I'll have the 1/2 out there, 0. And now when I try to plug this in, put it in here, you're going to get infinity squared, which is infinity still, but the negative will make it a negative infinity. Now you may be tempted to make this a plus and turn it upside down. While that's going to end up being true, that's not what you should do. You should evaluate each of these independently. Let's start this one here. The antiderivative of e to the u is still e to the u. Both of these are going to integrate exactly the same. Now let's plug them in. I can plug in 0, so I'll get negative 1/2 e to the 0 minus negative 1/2, so I'll have plus 1/2, and this time it'll be the limit as a goes to negative infinity e to the a. Well, as a goes to negative infinity, remember e to the a, that's the left side of that graph I showed you, that part's going to be going to 0. Same thing's going to be going on here. I'm going to have the limit. I'm going to use a again since it's going to negative infinity, e to the a, plus 1/2 e to the 0. Well, let's see what all of this has yielded. Negative 1/2 e to the 0. E to the 0 is 1, so this is negative 1/2. This piece right here is 0. This piece right here is 0. And this piece right here is positive 1/2. So they actually all cancel out and you end up with 0. So this integral converges. Not only does it converges, the sum is a 0. And that should make sense. Let's go back to the original function here. If I take an x value, plug it in, and then I plug in the negative of that, this piece right here will give me the same answer whether I plug in a positive or negative version of a number. However, this will keep track of that sign. What that means is together this is an odd function, which means that whatever happens to the left of 0 should cancel out what happens to the right of 0. It just so happens that that happens here because the area in the left was negative 1/2. That means it was below the x-axis. I'll draw a real quick graph here and you can see what's going on. This function does something like this. Comes through and does that. Odd function. So this area ends up being negative 1/2, while the area of the other side ends up being 1/2, and they cancel. But remember, you have to do these limits independently. Don't do one variable for both limits. Now, what you should do in all of these cases is still try to do these integrals as you're used to doing. For instance, I may allow u to equal x squared plus 1. Then du will equal 2x dx. Now, notice I didn't need 2x dx, I just needed x dx. So I'll divide by that 2 and get that. Now, what do you think happens to the limits of integration? If I take x equals 0 and I plug it into here, I will get u equal 1. Now, if I take x equals infinity and plug it in here, infinity squared, you should hopefully understand that's still an infinity. Plus 1 is just a little bit more of an infinity. So we have 1 to infinity. I'll put the 1/2 out front. X dx was my du. Part of the du anyways. And then u was x squared plus 1. So I'll have u, the fifth root of u in the denominator will end up being u to the negative 1/5. This applies to one of our situations here. I have negative 1/2 is less than 1. Since negative 1/2 is less than 1, this integral diverges. I'll sort of make it, it diverges because negative 1/2 is less than 1. There's no reason to even try to evaluate it anymore because it's going to be fruitless to even try. Here's an interesting problem. Tangent is defined when theta equals 0. In fact, tangent of 0 is 0, but tangent goes off to infinity as it approaches pi over 2. A quick, dirty little graph shows something like this. Pi over 2 is a vertical asymptote. The question is the area inside of here going to be finite or infinite? Well, that all depends on if this converges or diverges. Now, if you look at from 0 to pi over 2, it's often easier. In case you haven't seen this before, the way you integrate tangent is you break it up to this, into this, and then you allow u to equal cosine of theta, and then du to equal negative sine of theta d theta, so that I can rewrite this integral, have the negative in front. But now, if you plug in theta equals 0, cosine of 0 is equal to 1. If you plug in pi over 2, well, cosine of pi over 2 is equal to 0. Then I have 1 over u du. Well, I can simply rewrite this, take out the negative, and turn it upside down. Now, 1 over u has no problem with the number 1. You can't plug in 0, though. If you try to plug in 0, that will end up being undefined. So we have to do the natural log of u. No absolute values are needed once again. That equals the natural log of 1 minus the limit. As a goes to 0 from the positive side, ln of a. And we all know that as the natural logarithm tends to get close to the y-axis, it shoots off to negative infinity. So you get 0 minus negative infinity equals infinity, and this diverges. So there's not a lot more to it than that. I did want to bring you up with something. I did want to bring up something that was sort of paradoxical. And it's referred to as Gabriel's horn. This is the Gabriel from the Bible. So as you can imagine, the horn must be pretty spectacular. And what we do is, I want you to consider the region in the plane bounded by y equals 0, x equals 1, and y equals 1 over x. So the region I'm talking about looks like this. I'm going to have 1 and then a 1. So 1 to infinity, it's going to go off like this. It's going to taper down, but this is what it's going to look like. Now, that's a horrible, horrible picture, but there's more. Now, rotate that region about the x-axis. Well, you remember this game, right? Hopefully you do. Rotation will occur about there. What you'll end up having, I don't know if I'll be able to draw a picture. I'm somehow used to the other direction, but something like this, and then something like this. If I took away those arrows, let me take those arrows away. See if I can just erase that arrow part. I don't think, You can see that if this is small enough, this could be considered something of a horn, couldn't it? So, very long one since it goes off to infinity, but this is called Gabriel's horn. And the volume of that region, if I try to figure out its volume, we can use what's called the, if you remember, the disk method, because there's no hole in it. It's revolving around the x-axis. So the volume, that was the one that was pi r squared times delta x. So since we're starting here at 1, this would go from 1 to infinity. The r is simply 1 over x, so I'm going to have 1 over x squared dx. Well, this equals pi. Now this is x to the negative 2, so this will be pi times negative 1 over x. And that will be going from 1 to infinity. And as always, the 1 is no big deal. You're going to have, this will be the limit. As a go, let's make, since it's positive infinity, I'm going to make it a b, just to keep myself consistent. So pi over negative 1 over b. And then when I plug in the 1, I'll have plus pi. Well, this piece right here, as b goes to infinity, you're going to have a very large number being in the denominator. It doesn't matter that that negative's there. If you want, this will be negative 0 if that suits you. That'll equal negative 0 plus pi. Well, negative 0 is still 0. It equals pi. So Gabriel's horn has finite volume. However, next let me discuss the surface area of that particular horn. Suppose we wanted to paint it in a thin layer of gold. Let's electroplate in gold. That would have essentially no thickness. How much electroplating material would we need to do it? So this works out. If you'll remember, we have 2 pi, 1 to infinity, and then the first piece of it is 2 pi r, which is f of x. So f of x here was what? 1 over x? And then we have 1 plus the derivative of 1 over x. So if I take the derivative, I'll write it as x to the negative 1. Will be negative x to the negative 2. And you'll square that piece, dx. And that'll equal 2 pi, integral from 1 to infinity, 1 over x. And I'll end up with 1 plus x to the negative 4. And I'm actually going to stop right here. The reason why is because this piece right here is definitely greater than 1. Let's see if you can agree with that or not. No matter what x is, it's not going to be a negative number. It'll be, if x is 0, fine, this is 1. But anything else is going to add positive number to the 1. So I can say no matter what, this is greater than or equal to 1. But I should have said it's actually greater than, because x isn't even allowed to be 0 in this interval. So I'll actually take that away. The reason I write that is because this whole thing then is greater than or equal to 2 pi, the integral from 1 to infinity, 1 over x times 1 dx. And maybe I should warn you at some point, inequalities rule calculus. Everything, and I mean everything in calculus, is defined in terms of limits, and limits are defined in terms of inequalities. So the point I'm making is that this integrand is bigger than this integrand. So an integral that is dealing with only positive numbers and adding positive area to it as x goes to infinity is going to be bigger than a smaller amount of positive area being added. That made sense to you? Let me go ahead and integrate this. There is no need for the absolute values because I'm dealing with positive numbers. Now the ln of 1, of course, is equal to 0. But this piece, the limit as b goes to infinity of ln of b, is actually infinity. Because it may not do it quickly, but the natural logarithm does eventually get up to infinity as x goes to infinity. So, what do we have then? The surface area diverges. Here's what we have. Gabriel's horn can be filled with paint because it has a finite volume, but it can't be painted.